It's time to start looking at the various different pressure control modes, and the chairman of the board of all of these, of course, is pressure assist control. It's the original. This is part one of 2 tutorials on pressure assist control where I look at the use of this mode of ventilation in a patient with relatively normal lungs. Tutorial 23, Pressure Assist Control, Part 1. Previously, I did 2 tutorials on the fundamentals of pressure control ventilation. The second tutorial was principally about mean airway pressure, and I explained the importance of why you need to adjust mean airway pressure in the setting of the concept of phasic ventilation perfusion mismatch during inspiration. The mean airway pressure can be increased by increasing the Peep, by increasing the inspiratory pressure, but most effectively it's increased by increasing the respiratory rate or the inspiratory time in the setting of an increase in the I to E ratio. So by increasing the inspiratory time but reducing the expiratory time. We looked at how you can prolong inspiration in pressure control, and we looked at how you can do something similar in volume control, and I explained the differences between increasing mean airway pressure in pressure control and volume control and why they're different and why it's easier to do so in pressure control. This is one of the key tutorials in this whole series because in this tutorial I'm going to look at one of those foundational modes, pressure assist control, and how to set it up, the advantages of using it in low compliance lung states and high resistance lung states, and the limitations of using pressure assist control. First of all, I just want to show you one set of waveforms. If you were to look at a ventilator without being terribly curious and you looked at this waveform, you may be misinterpreting what's on it. And the reason why is when you see this inflection point here in the flow waveform, you immediately decide that this must be flow limited ventilation, in other words flow cycling, like you see in pressure support. But in fact, this breath here is a non-assisted breath. It's a controlled breath. So this is a control mode of ventilation where flow is shutting down. And I'll explain later in this tutorial what's going on here and why it's a problem and why most people miss this. You're called to the emergency department to see Carla. She's 44 and she's taken an overdose. She was brought in by ambulance and she's taken a whole range of different drugs. She's a history of asthma and mental illness. And when you see her Glasgow coma score is 4 to 5. She's saturating 98%, but she's not really protecting her airway. She is being intubated and has been commenced on pressure assist control. So when you start someone on pressure control, you need to set a number of mandatory breaths. This is a situation where the patient is probably not going to breathe properly for themselves, particularly if they're comatose to start with and you've administered anesthetic drugs to access the airway. So you need to control. The control mechanism here is pressure control. And when you put someone on pressure control, the targeted volume that you give, the tidal volume, is always variable, as is the minute ventilation from minute to minute. You must set a trigger, and the standard trigger is time on pressure control. But if you're using assist control, you must also add a way of triggering the breath by assisting the patient, and that can be a negative pressure trigger or a flow by trigger. Cycling is always time in pressure control. Pressure control is a time cycled mode of ventilation by definition. The flow is determined by the inspiratory pressure ramp and the rise time. All assisted breaths have the same characteristics as control breaths. That's the pressure limit, the rise time, and the inspiratory time. However, because there is a difference in the driving pressure, the tidal volume always varies. These are the parameters that you adjust when you are setting up pressure assist control. Firstly, you set up a respiratory rate because this is a control mode of ventilation. Then you set an inspiratory pressure. From that you derive the pressure limit, which is the Peep plus the IP. Being pressure control, you must have an inspiratory time. Then you set the FiO2 and the Peep according to the patient's needs. You adjust the inspiratory rise time or the slope, and this needs to be crafted for the patient. And if you expect the patient to breathe, which you should, then you have to set a trigger, and that can be a negative pressure trigger or a flow trigger. Here is a screen of a Puritan Bennett ventilator that you're setting up to put the patient on pressure assist control. So we start off here. Here's our control, pressure control. The type is assist control. There are alternative ways of delivering pressure control that we'll mention in subsequent tutorials. You set a respiratory rate. You set an inspiratory pressure. This is the IP. The Peep and the IP equals the plateau pressure, or the pressure limit as I prefer to call it. Here is the FiO2, here is the Peep, and here is the inspiratory time. They're the real core parts of pressure control. On modern ventilators, you also get to set a rise time. You should always set a peak pressure limit. This is important because if the patient starts to cough, you really don't want to be double breathing for the patient. So the ventilator should cycle off to expiration, and that's 35 in this particular setting. And here's how we're deciding to trigger this particular ventilator using flow-by triggering that I explained in one of the early tutorials. It's worth having a look at the setup of the Drager Infinity ventilator at this stage. Drager ventilators are very much set up to be pressure controlled, but the settings are a little bit different from other ventilator brands. And I'm just going to look at the basic ones here. There's a lot of advanced stuff in this particular ventilator. So you can see here, this is a patient who's on pressure assist control on this particular ventilator. You can see the typical decelerating flow pattern, the flat top pressure waveform, and the mean airway pressure it's quite nice here because it's related to the Peep and the driving pressure. So that shaded area in the pressure waveform is the positive pressure component, and you can see the little number for the mean airway pressure just to the right of the pressure waveform. The little arrow on the bottom right part of the screen leads to a pop-up screen that gives you the basic settings. And here they are. So on the left-hand side, we have the FiO2. This is just set at room air. The inspiratory time. The respiratory rate. The rise time, which they call the slope, and this is in seconds, so it's 0.2 of a second. Very nice way of doing it. You've got great control there. You have the Peep, and then you have another thing called the Pinsp, which is not the driving pressure. It's not the inspiratory pressure. In fact, it's the pressure limit. Let me illustrate this. Now on this picture, on the y-axis, we have pressure going from 5 to 25 centimeters of water. And I've split the screen into two different things. We have most ventilators on the left. In this case, we're just going to use the Puritan Bennett ventilator as an example, but it could be anyone. And on the right, we have Drager ventilators. And I've started off with a Peep of 5 centimeters of water on both ventilators. The ventilator on the left, which is the Puritan Bennett, has an inspiratory pressure of 15 centimeters of water. So when this ventilator cycles, the driving pressure is 15 and the pressure limit is 20, and that results in a tidal volume of 450 mils. Now the setting on the Drager ventilator to achieve the same 450 mil goal is different because you have to set a Pinsp, or a pressure limit, of 20 centimeters of water. So it looks different. That gives you the same driving pressure above Peep, which is 15 centimeters of water, and it results in the same tidal volume. Now we have increased the Peep to 10 centimeters of water on both ventilators. On the Puritan Bennett, the IP, the inspiratory pressure, is still set at 15. So when the ventilator cycles to inspiration, the pressure limit is 25 centimeters of water, the driving pressure is 15 centimeters of water, and the tidal volume remains 450 mils. On the Drager ventilator, we have not changed the Pinsp. So when we cycle the ventilator to inspiration, the airway pressure increases from 10 centimeters of water to 20 centimeters of water with a driving pressure of 10 centimeters of water, and this results in a tidal volume of only 350 mils. So it's important to understand that increasing the Peep does not nudge upwards the inspiratory pressure on the Drager ventilator. You need to increase the driving pressure independently. And while this is a good approach for preventing the unthinking crossing of that 30 centimeters of water Rubicon, it is something extra to think about when you're setting the ventilator, and mistakes may happen if there are multiple ventilator brands in the ICU. So be aware of that. When you're setting the Pinsp, it is not the driving pressure. It is the plateau pressure that you're targeting there. So let's have a look at inspiration in pressure assist control, and we'll start with the control mode. This is pressure assist control. You will note that the inspiratory pressure has been set at 15 centimeters of water. The rate is 15 and the inspiratory time is 1.2 seconds with a PEEP of 5. The control breath is triggered by time. The gas has been blended and the breath is ready to be delivered from the bellows or piston. So let's trigger the ventilator. Gas passes along the inspiratory tubing, and in this case it goes into an endotracheal tube. The lungs inflate and the diaphragm and chest will move downwards and outwards, so the thoracic pump in this control breath is entirely passive. The breath will register as a control breath on the ventilator. For example, you can see that C there on the corner of the screen. And once the airway pressure goal has been achieved, gas is held in the airways until the inspiratory time has elapsed. Sometimes the inspiratory time elapses before the inspiratory pressure goal has been achieved. On the waveform screen, you will note the triangular shaped waveform for decelerating flow. It reaches baseline at 0 flow and stays there until the end of inspiration. Also note the square-shaped or top hat-shaped pressure waveform characteristic of pressure control ventilation. Now we look at expiration. On expiration, the expiratory valves open and gas flows along the pressure gradient from high in the lungs to low, which is either PEEP or atmospheric pressure in the lungs empty. An expiratory flow waveform will register on the ventilator, as will the exhale tidal volume. And that's the number we want to see. Remember, we're only interested in exhale tidal volumes. It should correlate with the desired tidal volume, but that is not always the case. Now that's pressure control, but this is pressure assist control, so something slightly different must happen on the assisted breath. So let's add a patient participation element. Unless switched off by neuromuscular blockade or high-dose sedation, particularly with opioids, the human diaphragm is always in motion and the patient will want to take a breath. We're using flow-by triggering here, and the flow-by is traveling around the circuit at 2 to 5 liters per minute. When the patient takes a breath, note the negative deflection on the pressure waveform. The flow is deflected into the patient. The expiratory flow sensor notices that the return flow has dropped off if the deflection is of sufficient magnitude, and the ventilator, as you can see, has cycled to inspiration and a pressure-limited decelerating flow breath has been delivered. This assisted breath is different to the control breath due to the greater pressure ramp, and the tidal volume should be greater. You will note that there is an A on the screen that pops up to tell you that the patient's breath has been assisted. Again, expiration is entirely passive. It's all elastic recoil due to the increased pressure ramp, though that exhale tidal volume should be reading a slightly larger volume than the controlled breath. So the big difference between pressure assist control and volume assist control is the difference in the tidal volumes from breath to breath if the patient is assisting. In volume control, the assisted breath is a facsimile of the controlled breath. It is not the same in pressure control because of the increase in the pressure ramp. Now this is what pressure control looks like, and you can see from breath to breath there is a specific gap from one breath to the next when the patient isn't participating, and so the breath is triggered by time. In this situation, we have set an inspiratory pressure of 15, a PEEP of 10, and a 1.2 second I time. So you can see the pressure ramp here, where the driving pressure is 15 centimeters of water, giving us a pressure limit of 20 centimeters of water. Ventilator triggers and delivers a positive pressure breath up to the pressure limit, and it holds the breath there for the duration of the inspiratory time, which in this case is 1.2 seconds. One or two things to mention now. First, that the airway pressure and the alveolar pressure are not identical. This is what the alveolar pressure looks like. Secondly, in many ways the IP concept is misleading because it is the driving pressure that matters, and that's the true pressure gradient. With these settings, Carla is receiving a tidal volume of 450 mils, and if Carla, for example, has had neuromuscular blockade and is left lying in exactly the same position and there is no change to her lung morphology, well, she will keep getting 450 mils from this particular driving pressure, which is the inspiratory pressure above PEEP in the absence of auto PEEP. But if you add auto PEEP, for example, we know that Carla has asthma and has increased airway resistance and gas trapping, and she may have an auto PEEP of 3 centimeters of water. The next breath that occurs starts from the auto PEEP level, not the official PEEP level, with the result that the driving pressure has been curtailed to 12 centimeters of water. The airway pressure waveform looks the same as before, but the alveolar pressure, if you could easily measure it, it would demonstrate that the breath is starting from a higher pressure level. The inspiratory ramp is lower, so the tidal volume has fallen, even though the apparent inspiratory pressure is the same, the apparent PEEP is the same, and the inspiratory time is the same. When a patient triggers the ventilator, the driving pressure must change because the magnitude of negative pleural pressure impacts the alveolar pressure. The greater the inspiration, the inspiratory effort, the greater the pressure ramp between the alveoli and the pressure limit that has been specified by the ventilator operator. Of these two breaths, you can see that breath number 2, the one on the right, is associated with a greater inspiratory effort that is evidenced by that bigger negative deflection down from PEEP, and as a consequence you can see that the peak flow here is higher for the second breath than the first. If you translate that to tidal volume, because the peak flow is increased, the tidal volume will always be bigger in pressure control. And remember, the pressure control breath is time cycled. You take a bigger breath but for the same period of time as the smaller breath, and as a consequence the breath must always be bigger. Tidal volumes, as I've mentioned before, also change with changing the patient's position, with changes in their chest wall mechanics, with their lung mechanics, and with airway resistance. So if we look at what's going on with Carla, when Carla takes a breath, there's a negative deflection in the pressure waveform. At the very least in this situation, the driving pressure has increased to 18 centimeters of water, and as a result her tidal volume for the same inspiratory time and the same inspiratory pressure above PEEP is now 500 mils. The pressure waveform in and of itself is not always the same, and the inspiratory rise time, or the slope, is the time between triggering the breath and achieving the desired pressure limit. And this only applies to pressure control modes of ventilation. This is an example of the screen that we would like to see in Carla's case. You can see that she's on pressure assist control. She's on 18 breaths per minute. The inspiratory pressure is 10 centimeters of water. There's a PEEP of 5. Flow by is set at 3 liters per minute, and the rise time is 70%. And you can see that there's a lovely flat top pressure waveform, and the I/E ratio is 1 to 1.6. And this translates to a tidal volume of 434 mils, which is pretty good. And the compliance here at 56, that's up there, C-Dyne up there, is good but not stellar. The major method for crafting the inspiratory waveform is to ensure that the patient is triggering the ventilator effectively, and you can see that with this flow by of 3 liters per minute there's no real evidence of inspiratory desynchrony or under triggering. But the second component, of course, is the rise time. The rise time determines the velocity of initial gas flow. It needs to meet the flow demand for the spontaneous breathing patient, so you need a fast-ish rise time if someone is breathing on their own. For a non-breathing patient, the rise time needs to be crafted to ensure there's a flat top waveform. So depending on what your circumstances are, if your patient is paralyzed and they're not moving, they're not breathing, you might set a rise time at 50% or even lower if the lungs are very non-compliant. But then if someone is breathing themselves, you need to make sure you're able to meet their flow demands effectively and you don't get flow demand desynchrony. So you might go to 60% or 70%, keeping in mind that you might run into trouble. So in this particular picture, we're going to try and sculpt the waveform, and you can see we've set at the rise time at 80%, and let's give the patient a breath. And you can see here that this looks all wrong. There is a pressure spike, nothing looks right, the waveform is not flat topped, and it's likely that this patient may end up having pressure cycling very early in the inspiratory part of the cycle. So we go ahead and we drop this down to say 40%, and let's see what happens with 40%. Well, this looks all wrong as well. We now have this very strange looking pressure waveform that looks like an M. It's scooped out, and the reason why it looks like this is there is inadequate mid-range flow because the patient is not getting enough flow from the time that the ventilator cycles to where it gets to the plateau pressure, and that's because the rise time is set too low. So let's try again and set the rise time at 60% and see what happens. And you can see here that the waveform is perfect. We have a nice negative deflection and inspiration. Flow goes up very quickly up to the plateau pressure level, and it sits there. And that's what we want to see, and that's what you do with the rise time. The other thing that we need to look at is how the patient triggers the ventilator, and we're just going to mention in this component flow triggering. I did a tutorial on different ways of triggering the ventilator very early in this course. And the Puritan Bennett ventilator, a specific volume must be drawn to trigger the ventilator. So you might set this at, say, for example, 2 liters per minute or 5 liters per minute. And if you recall from that earlier tutorial, the lower that number is, the easier it is for the patient to trigger. The higher that number is, the harder it is for the patient to trigger. Now let's look at a flow waveform. On the y-axis, we have flow in liters per minute. And we've set a V-sense of 3 liters per minute for our patient. So let's start at the very basics here. The Puritan Bennett ventilator has a base flow running through the circuit at 1.5 liters per minute. You can do nothing about this. And the V-sense is set above this. So that's 1.5 plus 3 of V-sense. That equals 4.5. And 4.5 is the flow by in the circuit. This is the portion of the flow that you need to get to in order to trigger the ventilator. So the patient has to suck down through the V-sense to the level of the base flow to trigger the ventilator. And of course, the higher the V-sense is, the higher that amount of flow that you need to breathe through. So the closer that blue line is to the red line, the better the patient is in terms of triggering the vent, but there's also risk of over triggering. So 3 is a fairly nice place to start. And let's see what happens with Carla. So she takes a breath, and of course you can see here that her inspiratory effort goes right down to the base flow level, and that triggers a breath. If she wasn't triggering a breath, we would have reduced the V-sense to, for example, 2.5 or 2 liters. And if she was over triggering the ventilator, for example, just cardiac oscillations by triggering the vent, we might increase it. Just to illustrate here, so the base flow is 1.5 liters per minute. The V-sense is 3 liters. So that's a total of 4.5 liters. To trigger the ventilator, the patient demand must exceed 3 liters per minute. Crafting the flow waveform. Normally, when we breathe in, we breathe out almost immediately afterwards, and then there's a bit of a gap between the end of exhalation and the next breath. But normally it's a continuous cycle: inspiration, expiration, inspiration, expiration. There usually is not a pause at end inspiration. That only happens during mechanical ventilation. So this is what the waveform of a patient on pressure control should look like. You can see the flow of gas goes from zero flow up to peak flow, and then it decelerates down to the zero flow point again, and then goes immediately to exhalation. And this is the same whether the patient is breathing spontaneously or whether the patient is not. And that's why you can see here with a slightly bigger pressure ramp in the middle breath, the patient gets a slightly higher tidal volume, but the waveform looks the same, just slightly higher in terms of peak flow because of that pressure ramp. Now I showed you this at the beginning of the tutorial, and you can see here that the flow waveform is shaved off here before it returns to the zero flow state or the baseline state. This is not normal in pressure control, and it means that the breath has ended before the alveoli have all seen the target airway pressure. And this will happen due to two potential factors. The first is that the inspiratory rise time is too slow. The second is that the inspiratory time is too short. Regardless of whether it is the first or the second factor, the time from the beginning of the breath to the end of the breath is too short, so we need to increase the inspiratory time. Clearly, the 0.8 second inspiratory time is inadequate, so let's increase the I time to 1.3 seconds. Now you can see that the tidal volume has increased substantially from 360 mils to 480 mils, reflecting an increase in the mean airway pressure. However, we may not necessarily want the situation where there appears to be a significant inspiratory hold. Certainly, for hypoxic respiratory failure, this approach may be effective, but there is a risk, as we shall see, of expiratory dysynchrony. And briefly, what that means is that the patient may want to exhale before the end of inspiration that has been forced on them by a set inspiratory time. So let's pick a shorter time, in this case 1 second. Yeah, and this looks good, right? So the inspiratory flow goes down to baseline, followed immediately by expiration, and this mirrors normal breathing. Now in this situation, the flow waveform does not return to baseline, that is zero flow in expiration. In other words, expiration has not finished before the next breath starts, and this of course is representative of auto PEEP, and we must decide whether this is a problem or not. If the current vent settings are what you desire, that is the I time and the respiratory rate are where you want them to be, you're achieving the tidal volumes that you want, or you may not achieve those volumes, then the extrinsic PEEP can be reduced to be replaced by permissive auto PEEP. Otherwise, we need to lengthen expiration. And the first way we can do this is by reducing the inspiratory time. Now in this picture, we have reduced inspiratory time to 0.8 seconds, but not only was this ineffective at reducing auto PEEP, now we've run into the problem of inadequate inspiratory time with this whole shaving off problem of the flow waveform. So what do we do? Well, we first of all need to restore the inspiratory time to where it was so that we can get the full benefit of inspiration, but we need to reduce the respiratory rate to increase the I to E ratio. So let's return the I time to 1 second, for example. If the respiratory rate was 20 breaths per minute, the I to E ratio was 1:2, then we have a 2 second expiratory time. But that was causing auto PEEP. If we reduce the rate to 15 breaths per minute, that is a 4 second cycle and a 1:3 ratio, there is 3 seconds for expiration, and that might just work. If the rate dropped to 10 and then the ratio was 1:5, you've got 5 seconds in expiration, and that should be plenty. If this proves inadequate to control PaCO2, consideration should be given for increasing the inspiratory pressure. Having crafted the inspiratory rise time, the tidal volume based on driving pressure, and the PF ratio based on PEEP, we have reached these baseline settings. Remember that our goals are a tidal volume of 450 mils or 6 mils per kilo with a PaCO2 of 40 millimeters of mercury or 5 kilopascals, and a PaO2 of greater than 80 millimeters of mercury or 10 kilopascals. And obviously there is a fair amount of wiggle room in these settings. This graphic demonstrates the relationship between tidal volume on the y-axis, and it's going upwards as you go upwards, versus the I to E ratio. This is the ratio between inspiratory time and expiratory time. Now I'm just going to roll this out and watch what happens. We're going to start here in the middle, and the curve will go downwards on both sides. From the base point here of an I/E ratio, for example, of 1:2, as the inspiratory time shortens, that means we're going to the left on the graphic, the tidal volume drifts downwards progressively because the inspiratory time is too short. On the other hand, if you go from left to right from the apex of this curve, you can see that the tidal volume goes up initially as you go to, for example, a 1-to-1 ratio, and then it starts to fall progressively. And the reason why is that the expiratory time becomes too short and the patient starts to develop a lot of auto-peep. And auto-peep, as I've mentioned many times, causes the driving pressure to fall. Let's just illustrate this. Now on this graphic, on the y-axis we have the flow in liters per minute on the top, and then the tidal volume in mils on the bottom. And you can see there I have 450 mil tidal volume and a line drawn across the screen, and that's our target tidal volume. Now I'm going to start with short inspiratory times, and then we're going to progressively increase the inspiratory time with a set I/E ratio of 1:2. And let's have a look at the impact on the tidal volume. So it starts off and the tidal volumes are poor, 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 and then they start to improve, and then they fall off again, just like in that U-shaped curve that I showed you before. And this green loop here is around the ideal situation. This is where she's getting her 450 mil tidal volume. The flow waveform is coming down to baseline, and there is no potential here for her having expiratory dysynchrony. Yes, as you move to the right, you get a slight increase in the tidal volume due to the increase in mean airway pressure, but there you start running into trouble. And then subsequently, of course, the tidal volumes drop due to auto-peep. Again, on the left-hand side of this loop, there is inadequate inspiratory time, and on the right-hand side, inadequate expiratory time. Let's just summarize this part of the tutorial. Just because you set an inspiratory time for the patient in pressure control and the lungs are compliant does not mean that the tidal volume goal will be achieved. You need to craft the flow waveform to ensure that inspiratory time is sufficient to ensure adequate tidal ventilation, but not too long as to promote auto-peep. One thing that I've pointed out at every single stage of this series is the importance of looking at the waveforms on the ventilator. Without looking at the waveforms, you are blind. We can now review this tutorial. In this tutorial, I talked about pressure assist control, and this is the first of 2 tutorials. And this tutorial is really about looking at the basics of using this mode of ventilation in a relatively healthy set of lungs. So I talked about setting up pressure assist control ventilation, and then we looked at airway pressure, alveolar pressure, and driving pressure. We talked about tidal volume variability and pressure assist. And pressure assist is when the patient takes a breath on pressure control, and I described why the tidal volumes are greater than with a controlled breath. I discussed crafting the pressure waveform, crafting the flow waveform, and I explained why tidal volumes are low with very short and very long inspiratory times. Next time, I will discuss the use of pressure assist control in acute hypoxic respiratory failure. We'll start with increasing the inspiratory time and gas distribution for both low compliance and high resistance, pressure control when hypoxemia progresses, the problem of transpulmonary pressure in pressure assist, and then we'll talk about why inverse ratio ventilation is really effective in pressure control modes of ventilation. I'll talk specifically about pressure assist control. Join me then, and I guarantee you'll learn something. So that was part 1 of 2 parts on pressure assist control. Next time I'm going to discuss pressure assist control in acute hypoxic respiratory failure. If you're enjoying these tutorials, don't forget to subscribe on YouTube or follow me at ccmtutorials.org.